All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. It's really pouring outside right now. And I rode my bike here this morning. It wasn't raining when I came, and I consider that a win. At least when I'm going home, I'm planning to have a shower anyway. So, now I can skip the shower because I'll be all clean from the rain. Welcome everyone to class. I hope that you are all doing okay. Today, we're going to be working on code eventually from last class. So both strings.c and lineinput.c. So while we're getting started with some other stuff, if you would like to follow along with what we're working on today, please make sure that you have those available, either your own copies or what I posted to the course webpage yesterday, so that you can follow along with what I'm doing today. So today, what I want us to be able to do is I want you to be able to get line-based input from standard input with fgetS. We did get to the end of this last time. We got to the end, but there are some small things that I want to touch on before we leave this behind. I want you to be able to describe concepts of in-application memory management, such as the runtime stack and the heap. This is like we're talking about C-specific stuff. We're going to move and talk a little bit more abstractly about memory. We're going to start by talking about memory in the context of arrays in C. We're going to move to talking about memory from the perspective of an operating system, but we're just scratching the surface there. You will learn a lot more about memory from the operating system's perspective when you take operating systems in third year, but I want you to have a really high-level idea of where things are in physical memory. That's what I want to be able to do here. I want you to be able to visualize and describe parts of a standard memory layout. So this is from an entire blob of memory, like the all working memory that you have in a process. I want you to basically be able to describe and visualize, so draw a picture of the whole memory layout of a program that's running. I want you to be able to visualize and describe how the stack changes as functions are called. So as we're calling functions, what's happening to the runtime stack? What does that look like in memory? And then what are the consequences of what's happening here? So why are we observing some strange behaviors or some unexpected behaviors when we try to do certain things? I want you to be able to write code that takes advantage of its environment through the redirecting of standard input and output for file I/O. Again, we did touch on this last time, but I just want to make sure that I'm formalizing it. We're going to do this more throughout the term, so I just want to make sure that we have a firm idea of what's going on there. But before we get to any of that, I would like to give you some time to ask me some questions about assignment 1. We'll take as much time as we need. Assignment 1 is due on Friday, so you've got a couple more days. If we're thinking in terms of like clock time of a regular term, there's a whole week left, but that's not realistic. So we've got a couple days left before the assignment is due. So yeah, please go ahead.
Yeah, 2 questions.
Sure.
First one, for the magic characters, which ones do we need to define and which do we not? Do we need to define them for the braces, for a space character, for probably need to do the T and the F, but which ones do you which ones?
That's a good question. So I'm going to try to summarize it. Please correct me if I'm misrepresenting what you're asking. The question is about how much detail or how far down do we have to go in terms of declaring constants using preprocessor directives. So the 2 that come to my mind right away are you should be using preprocessor directives for the color changing codes. So those are declared as static variables in the Java program. Those kind of jump out immediately as those should be preprocessor directive constants. In terms of T and F for true and false, yeah, those should be defined as constants. It would be reasonable to define those as constants. If you're talking about brackets, you can go to the extent of saying something like right paren and left paren, or right bracket, left bracket. But in this case, I would say what the Java code does is an acceptable practice. So if the Java code is not naming a constant variable for those characters, then it's okay to just use those characters. For null, null is there already. You can use uppercase NULL. That's just a named constant that you have access to without you defining anything. Were there any that I missed that you specifically wanted to know about other than that? New line and space. So the same kind of idea. If they're not defined in the Java program, space specifically, and in the context of separating the characters out, separating the two fields out for the file reading thing, a space, you can say, call it separator if you want. Yes, yeah. That was your first question.
Yes. Is it just in general a good idea to have a function? Last class we talked about how we can't return arrays, but we can set the array within like the contents of the function.
Yeah.
Is it a good idea to have that and then also have that function be able to return, say, a length?
Okay, so that's a really good question. The question is, should we design our API? I'm going to say it that way. Should we design our API? Should we design our function signatures so that they take as input an output argument? So what we did last time with string copy is we've got an array that we're going to write into and an array that we're going to copy from, but should it also then return an integer or some other kind of primitive variable or some kind of primitive type? It depends. It really depends. So fgetS is a good example of this. fgetS takes as input an output argument. You pass a buffer to it, but then it also returns, in this case, a pointer or null. Should you write something that returns how many characters you copied? Maybe, if you think that's something that you need to use in the code that you're doing. You're designing this right now for yourself. So if you think that you need to have how many characters, as an example, that you copied, or how many characters that you have maybe taken a substring of, that sort of thing, then sure, you can put that there, but it kind of depends on what you want. In general, I'm going to say that a function should do one thing, and it should do that one thing well. But in cases where it makes sense to have two pieces of information from the same single operation, then yeah, it does make sense to do that. Good? Okay. Yeah. How do you count the characters in a string with a null terminator in it? You go 1, 2, 3 on your fingers like this, and then you hard code the number 3. So I'm sorry, I'm being maybe, I hope not too mean. I'm not intentionally trying to be mean. I'm trying to be funny, but maybe it's not coming across as funny. Thank you. In this case, for this assignment, I would really just strongly recommend that you hard code the length of the strings and that you change all of the function signatures to accept the length of the string as input. In terms of, and I'm going to pre-answer this question in case anybody does ask it, because it's been asked on the forum once. It's been asked on the forum once. Your question is kind of related to, can we use string.h for this assignment? And I'm not forbidding you from using string.h. And in fact, I'm going to go out on a limb and say that in the future, you should definitely just use string.h. But for this assignment, I've forced your hand, and I've very intentionally put that null byte in there because Java treats its strings differently. It doesn't care about null bytes. And with Java, you've got an object that knows its own length, so it doesn't have to use terminators like we have in C with that null byte. So the short answer to your question is just hard code it, hard code the length. If you want to use something like strlen for calculating the length of the hand, the power, oh my God, the infinity gauntlet, if you want to use strlen to just compute that and print it out and then hard code it in your code, that would be perfectly acceptable. If somebody wants to go through the process of telling everyone else what all the lengths are supposed to be on the forum, that's totally fine with me. That's not sharing code. But yeah, change the signature of the functions to accept a length argument, and then use that length value in all of your code. Don't rely on strlen, don't rely on any of the other string functions for that. So hard code all the string lengths, yes. And then you don't need to declare constants for those, to be clear. You can just put that number beside it and it's implied. Yes?
Not that I'm using VS Code, but if you're in VS Code and you hover your mouse over the character or the string,
Okay.
it'll tell you the length of it. So you don't need to like count it. So
Okay.
you know,
If anybody else is using VS Code, then they can do that. Is that what you're saying?
yeah.
Yeah, okay. Okay. Yeah.
So to repeat his question, the solution to statement, you said the length, right? Hard code the length.
Yes. Hard code the length.
What kind of length?
So hard coding the length here is just going to be, you're going to add another parameter to the function. So there's that function test balance. You're just going to have to add another argument, another parameter to that function when you declare it. Same thing with is balanced. You're going to have to add parameters for length so that you're using the length of the string that's been passed and not trying to compute the length of the string with strlen. Yeah. Yeah.
Like last class we did a function that just counted up to the null character. I just used that function. Just put it in as an argument.
That will not work for the last test case. Yes, the last test case has a null byte in the middle of it, and so it's actually 3 characters, but when it counts it up using the null byte as a terminator, it will count 1 character. So that last test case should not fail, that should pass. Yeah.
So when printing out the results, especially for the one that has a null byte in between,
Yeah.
it's okay to print
So when you're printing out that last test case, the one that has the null byte in it, this is a place where it might make more sense to print character by character to the hard-coded length as opposed to using printf with %s. Printf with %s works the same way that all the string functions do, in that it stops when it sees that null byte character. So if you print it with %s and printf, you're going to get just the opening parenthesis and then not the rest of it. So for that one part of it, for that one part where you're printing out the string that's been provided to the test function, you should print it out character by character for the specified length. And when you do that, then it will print out it will print out 2 parentheses next to each other, but there will be a null byte in between, which is what it looks like for the Java output. Yeah. Yeah. So basically, you're supposed to make a 2-string. Sorta, yeah. You're supposed to make a string printer that just prints out characters, a character printer. Let me call it that. Make a character printer that prints out the specified number of characters from an array.
When commenting the functions or just putting the outline for it, can we just sort of steal your write-up for test balance?
Yes. So the question is, when we're printing out, or when we're putting comments on a function, can we just start with what's in the Java code? 100% yes. You need to change it because you're going to be changing the function signatures, but the purpose of the function is identical to what the Java program does. Yes. Yeah.
Someone just texted in the chat. Is there something like string split in C or string dot split?
That's a good question. So is there something like string.split in C? Yes, it's called strtoke, and you should not use strtoke for this code. strtoke is string tokenization, and that's what split is doing on Java string objects. The difference between Java string objects and str token C is that string.split returns an array, which we can't do in C. String tokenization will basically, it works by destroying the string that you pass to it. So string tokenization works by inserting null bytes into the string that you pass to it. And so if you insert null bytes into, if you are calling this and it's inserting null bytes into the string that you're passing to it, it's going to mess with a lot of stuff. My advice to you for this part, for getting like read up to one part and then read the next part, this is not a split operation. Yes, that's how I would do it in Java 2. But in C, the way that I would approach this is that I'd have effectively a flag that says, I'm going to start with writing into this part. I'm going to start by writing into this variable, copying into this array, this string that I've got. I'm going to do this until I find a space character. When I find a space character, then I'm going to flip and I'm going to start reading the next thing, which is that single character. That should be the last thing that's left, is just one character after the space. I can read that single character and then decide whether this is a true or a false, T or F, or if it's neither of those things, and then skip the output if it's neither of those things. If I get into a situation where I get to the end of the string and there's no space, then it's not a valid line. If I get to the end of this thing and it's not a T or an F, it's not a valid line. Yeah. So kind of like don't use strtoc. Just do it the kind of the dumb way. What seems to be the dumb way. Yeah. Yeah.
Is it slower to use fgets if we're have to read in a whole line and then also copy parts of that line over to another string, or is it fine to use fgets for this assignment?
Is it slower to use fgets?
Like rather than get char?
Rather than get char? The speed of this assignment is not important. It's irrelevant. I mean, if your program takes 2 minutes to run, that's a problem, but it should finish like instantly as far as we as humans are concerned. Is it faster? You know, ultimately my answer to this question in the context of this course is use the thing that's the most readable, whether it's slower or faster, and then we can change how it works later to make it faster if it is so slow that it's unusable. It's kind of a non-answer, I realize, but I hope it's enough of an answer. Yeah, okay. Yeah.
So, can we decide this here above, right? And head above when we say just a line, and simple line or say keyboard or whatever it is, text bar.
Yeah.
You name that crowd. Can we use it as a pointer? Can we point to that line? And do that as a limit bar?
So, so the question is, I'm going to summarize the question as, can we use pointers in this assignment? I'm not going to say no, but it's going to be a little bit more difficult to read, and it might lead to more issues than you're expecting if you use pointers to solve the problem. Yes, you can use pointers to solve this problem. You can use ultimately one single array and pointers to solve the problem, but that's going to be, it can be difficult to work with compared to just using arrays and passing arrays around. Any other questions? Yeah. Is it okay to use scanf or scanf? No, just don't. And we will see why. I will show you why. I have intentionally chosen to show you fgetS to begin with. Scanf, scanf, getS. These are all functions that can get strings as input, but they're real bad at doing that job. fgetS does the best practice that I've been suggesting to you of accepting as input how many characters it's allowed to read. Scanf, scanf get S do not. They just blindly write as much as they can. So please don't use S scan F. Yeah. All right. We're okay? Okay. I am going to have office hours today. I will have office hours on Thursday. The discussion forum is available for questions. I'll be able to answer questions to that on Friday. I will be unavailable for a little bit on Friday because my high school teacher is coming with a bunch of students to campus on Friday. If you went to Sturgeon, Mr. Wax is coming. Did any of you go to Sturgeon? Nobody went to Sturgeon. I didn't go to Sturgeon either. I went to a school called Silver Heights, and then it got torn down. And they merged. So there was two separate schools. Now I'm super digressing. There were two different schools in my area, two different high schools. There was Silver Heights and then Sturgeon Creek High School. Sturgeon Creek was built, I think, in the 80s, and Silver Heights was built in like the 50s as an elementary school. But I was there in high school, and it's built as an elementary school, and so all the water fountains were down here. And so, like, if you wanted to get a drink of water, you had to bend over because it's for a bunch of tiny children originally. And surprisingly, they tore that school down because it was 50 years old or more, and it was just falling apart. And then they merged with Sturgeon Creek because Sturgeon Creek was mostly empty. I think at the end they had 80 students for a school that had supposed to have a capacity of like 1,000. So, and Silver Heights had over 1,000 students in a tiny elementary school. And they named this merged school Sturgeon Heights, which is just the stupidest name. And it's like this compromise, but all I can think about when I hear Sturgeon Heights is a bunch of like rotting fish up on a cliff somewhere. Welcome to Comp 2160, everyone. Okay, so I would like to get back to doing F-get-S here fairly quickly. I want to spend some time kind of fixing one of the issues that I've got with this right now, and that is that F-get-S here, when we've got this code, is just going to stop and then nothing gets printed to the screen. Is just sitting there and waiting for me to type stuff in, but I'm not being prompted for anything. I want to fix that, and by fixing it, I want to introduce a problem to demonstrate something about what's going on with F-get-S. So like I said just before class started, I'm going to be working with code from lecture 5. I'm just going to copy what I have from lecture 5 into a new directory. You might have this already if you downloaded it from the course webpage as a starting point. Please make a new directory for this lecture. But I'm going to say cp-r copy recursively lecture 5 to lecture 6. I'm going to change into lecture 6. The code that I want to work with right now is lineinput.c. And the things that I want to do to this is I want to add a prompt. So before we are asking for input, I want to say, hey, please enter some input. So I'm just going to do that very quickly right now. I'm going to copy this and paste it down here after I do output. And the last thing that I want to do is I want to put an exclamation point here. I'm going to put 7 exclamation points here just to be really enthusiastic about it. I'm going to put 10 exclamation points here because I want to be extremely enthusiastic about it. And I'm going to pop open a new terminal. I'm going to change to that directory, so comp 2160, lectures, lecture 6. And I'm going to compile this code. And I'm going to run it. So now it looks a little bit nicer. I'm going to enter my name. I'm going to enter my cat's name. Okay, good. I've sort of fixed it, and I've sort of introduced another problem here. When you are reading with fgetS, it's reading the file. And again, remember that in this case, the file here, this is stdin, this is standard input. That's the file that we are reading right now. When we use fgetS, it's reading the file and it's writing into the buffer until one of 2 or 3 events are happening. One event is it has read this many characters. So we're passing this thing into it and we're saying, I want you to read up until this, or a new line character, so they press enter on the keyboard, or there's nothing left in the file to read. When it reads up until a new line character, so my name, Franklin, has 8 characters, which is much less than 50. When I press new line, the new line becomes part of what fgetS is reading. So it's reading FRANKLIN, new line character. The new line character is also written into the buffer. It's also written into the buffer. So the very last character that we've got in here is going to be that new line character. I want to really quickly visualize this. Really quickly visualize this. So when I've got this name array, you've probably seen these visualizations of arrays before. Name here is this really long thing. I'm not going to draw 50 spaces, so I'm going to do this ... to 50. When I enter my name, what's being inserted into by fgetS into the buffer is all of the characters. It's inserting the new line character because I pressed enter on my keyboard. So \n, and it's then finally inserting a null byte at the end. So it's inserting 2 extra characters. The new line is coming from me pressing enter. I'm getting a phone call from a 509 area code. I don't know where that is. It's a scam, probably, yeah. This is me pressing enter here. This is me pressing enter on my keyboards that has that added to the buffer. This is inserted by fgetS. This is inserted by fgetS to say, this is the end of the string that I read for you. It's not all the way up to 50 characters, but this is as far as I got. When you pass 50 to fgetS, what you're saying is you have 50 bytes or 50 characters to work with. It may not put the new line in because it doesn't read the new line within that 50 characters, but it does count the null byte as one of those 50 characters. So it would be able to read up most 49 characters before it inserts the null byte. So let's switch back here. The solution to this is really just to replace the last character with a null byte. I'm going to now switch to using strlen from string.h for this problem. For this specific example, I'm just going to use strlen from string.h. I don't want to rewrite that string length function over and over. So I'm going to go back to my code. I'm going to include now string.h in this code sample. String, not strong. And what I need to do here is I need to say name at the character that I want to replace is just the last one that's in the buffer, strlen name, with a null byte. So I'm going to hit Control D on my keyboard here. I'm going to use up arrow to recompile it. I'm going to run it again. I'm off by 1 here. I'm off by 1 here. The very last character of the string, so strlen -1. This okay with everyone? Yeah. Yeah. So what we've done here is I basically changed this to be that. So now I've got 2 null bytes that are right beside each other. Does it affect anything? So having 2 null bytes beside each other, all it really does is it's made the string seem like it's one less character to all the string.h functions. But having the 2 null bytes beside each other, it's kind of irrelevant. Yeah.
So essentially, the right way to use STR domain. The right way to use it instead of just using it in using it to like point it to something or using it in a function.
Sorry, can you repeat the first part of your question?
So essentially, we're getting on how to use strlen from string.h.
So strlen, in the assignment, I mean, you can use it for parts that are not the test cases. The test cases is really the one place where you cannot use it. If you want to use it for other parts, like computing how long the string is that you got from fgetS, be my guest, yeah. Okay, so that's that. The other thing that I want to try here is I want to change this to be 5. So I'm going to make a buffer that's got 5 elements in it. So my name has enough space for 5 characters. One of those characters must be the null byte. Our strings are null byte terminated, so it must be the null byte. I'm going to hit Control D on my keyboard. I'm going to use my up arrow to compile this again. I'm going to run it. Okay. fgetS it's only going to read as much as you tell it to read. If you tell it to read 5 characters, it will only read 5 characters the first time that you call it. All that other stuff that I typed in, so when I go back here, I have typed in FRANKLIN, and then I pressed enter on my keyboard. That's a total of 9 characters. fgetS is going to read up to FRAN. It's going to say, okay, I need to insert this null byte into the string to make sure that it is a null terminated string. And it's going to leave the rest of what's on input still there. It's not going to do anything with it. It's just going to stay there hanging around until the next time fgetS gets called. So what's happening here is We type a bunch of stuff in here and press enter. fgetS is only taking some of it from standard input. It does this stuff, and then it goes back to the beginning. Immediately, fgetS is able to continue reading stuff from standard input and then do stuff with it. And then it goes back up to the top. The keyword here, the keyword that I'm going to use and the keyword that you're going to hear again in operating systems is that fgetS is a blocking operation. Blocking means, in the context of everything that we've done so far, when we get to line 16 in our code, code execution stops. So when I bring this back, I'm going to hit Control-D again, clear it, run it one more time. This blinking cursor right now is stuck on line 16 and waiting for me to do something. It's waiting for me to press enter on my keyboard. As soon as I press enter on my keyboard, it's going to start doing stuff. And when we get back up to line 16 here, if there's still more input on stdin for fgetS to read, it's not going to block. It's not going to stop and wait for me to type more in. It's just going to keep working with the next little bit of input that it's able to work with until there's nothing left. And then it will stop again, and it will wait for me to type more stuff in. This is a little bit of a problem. This is a little bit of a problem for us. It's a little bit of a problem for us because I'm not going to draw what's in name over time because we can kind of imagine what's happening. It's taking just one chunk and then the next chunk and just overwriting what was there before. The solution to this problem is, for now, just know in advance how many characters you're going to be reading in on every line. For now, just know in advance how many characters you're going to be reading in. Which is why in assignment 1, I've explicitly said you can expect that there will be at most 100 characters on a line. That's the maximum line length. That's the size of the buffer you should use. That's the number that you should be passing to fgetS when you're reading files for input. Later, when we're thinking about dynamic memory allocation, so when we are going to extend what we know about the C universe, we will have a solution to this problem. But for now, it's just know in advance how much you are expected to have as input. fgetS will read up until that maximum number, but it may not fill the entire array. So in the case where we have something that's much less, it just puts that null byte character somewhere in the middle. So it's partially filled array using that null byte as a sentinel character. Any questions about that? We're all good? Okay. When we're thinking about strings, when we draw pictures that look like this, did you ever see this in 1010, 1020, something like this? Yeah. When we look at these diagrams, we are indeed visualizing memory. We're trying to take some abstract sense of what's going into memory. Usually when you see this in courses like 1010, we're annotating it with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, ... We're annotating it with those indices. This is a really, really tiny view of memory, but it is a view of memory. It's an abstraction of what's in memory, but it's a view of what's inside memory at a kind of quite a micro scale. I want to take a little bit of a step back, and I want to look at this from the perspective of an operating system. I'm going to use another couple of keywords here that I probably won't use again in this course. But when I run this program, so I have this program called line input. I'm going to do ls-l line input. Line input here is a file. I'm going to call this, a program. When I run line input, I'm asking my operating system to read that file and run the code inside of it. These are two different ideas that are all revolving around the same kind of unit. Line input is a program. When I ask my operating system to run it, it becomes something called a process. Now we have a running program. It's a process. When a program is running, the operating system and the physical memory that are on your machine are now available for your program to start working with. The process is able to start working with memory in the operating system. I'm going to scroll up here a little bit. And what I'm going to annotate, I'm going to label this diagram a memory layout. I'm going to call this for a process. Or from the OS. This is a RAM. This is a RAM. But what I really want to show you is this right here. Not everybody opens their laptop and looks around inside. Not everybody opens their desktop and looks around inside. This is memory. This is what we're talking about physically when we have memory in a machine. On some machines, it doesn't look exactly like this. On some machines, it's actually just these chips here that have been put onto the motherboards, the main board of the machine, put onto the main board of the machine. On desktop machines, these modules can be plugged in as expansion cards to expand how much memory is available to your system. On a laptop, sometimes there are some expansion ports on the main board to put these things into. Most of the time, it's just those chips that are just attached directly to the main board of the laptop. Those chips are the literal physical view of what memory looks like. We could get even further down, and it doesn't exactly look like this anymore, but this also used to be what memory was. There's these wires that are going and they're crossing each other, and there's magnets that are kind of going around the intersections. And the way that memory works is that it's measuring what's at the intersection, the polarity, thank you. It's measuring the polarity at the intersection of those, using those magnets, and it's able to infer whether it's a 1 or a 0 based on that. Memory doesn't exactly work like that anymore, but I'm told there was a factory in Winnipeg that used to make that stuff, which is kind of cool. This is a physical representation of what memory looks like, but I want to look at this from an abstract point of view. So again, kind of from the perspective of an operating system. Yeah. That's a fair question. This is outside the scope of the course, but it's a fair question. The difference between laptop RAM and desktop RAM is literally just the shape of these expansion cards. As far as I'm concerned, there might be actual physical differences between them, but the reality is that it's like these chips. These chips are going to be the same as they are on a laptop as they are on a desktop. Desktops just have more physical space to put more chips on a single card like this. A laptop module is going to be quite small. It's about half the size of something like this. This is not to scale, by the way. Thank you. Yeah, this is not to scale. This is the physical view of it. That's not really what our process sees. That's not really what our program sees when it's running. I'm going to draw a layout here that is what an operating system enables a process to be able to see. I'm going to draw memory in this shape. I'm drawing it vertically instead of horizontally, the way that we've always seen arrays when we're imagining them. When an operating system makes a process, it's giving it access to memory. The way that an operating system gives access to a process to memory is in a series of different segments. I'm going to separate these. There's different parts of memory that we're going to talk about. This part of memory here, this is the code segment. In the code segment is your code, literally your code. So inside here is int main void it's not actually C code. It's assembly language code. It's bits and bytes. But ultimately, what we have in this section is a program. This section down here is called the stack. You've probably seen the words runtime. I know you've seen the words runtime, but maybe in the context of the word exception as opposed to anything else. Have you seen the words runtime stack all stitched together in a row before? Yes? Okay. From the perspective of a process or a running program, the stack lives at the very bottom of memory. The other part of memory here is called the heap. And I remember that you said you've seen this word before as a data structure in some cases. So if you've taken Comp 2140 already, you've seen this word as a data structure. In this course, the heap is just another region of memory that we are able to use. So far in this course, I'm going to put a red mark kind of around this one here. So far in this course, we have exclusively been using the runtime stack. And we have been using the code section. We're going to use the heap. We just haven't gotten to that point yet. We may have used the heap by calling functions, but we haven't really explicitly used the heap in our own code yet. Memory, from the perspective of our program, is accessible by addresses. This entire thing here, I'm going to use another word here. This entire thing is called an address space. This whole thing is called an address space. Again, you will see more of this in operating systems. We're just going to call it an address space and accept it as such right now. The address space for a program or a process starts at 0 and it goes to, I'm going to say, F, 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 F. I'm using a different number system to talk about addresses. Address spaces are generally described using hexadecimal. This is base 16. Do we know hex? Some of us, all of us, yes. Okay, do we know how to go back and forth between hex and decimal? Yes, you've done that before? Do you know the little trick to draw the table out? Oh, there's no table. There's no trick. For hex, it's just 0 through F. Yeah, 0 through F. Okay, good. Then I'm not going to draw the table. I'm just glad that we all know this already. All addresses here are going to be accessible by an address. All the locations in memory are going to be accessible by an address. The code section here in this diagram would be at 0x000. So when I write hex, I write X in front of it to say this is a hexadecimal number so that when you look at all zeros, you know it's not a decimal number. When I write 0xFFFF, I'm saying this is kind of like the top of memory. FFFF gives us, I think, 16 kilobytes of address space. My machine here has 24 gigabytes of address space. Your machines probably have 8, 16, 24, 32, 64, 12. Nobody is like insane enough to run 64 gigs in a laptop, are they? Good, I guess. I don't know. Good. Okay, so we've got this address space. This address space, I'm going to zoom in here just a little bit. This address space is filled with individual locations where each of these has an address. Every one of those little slots has an address, and you can access one single byte at a time. You can get down to accessing one single byte at a time. When we're drawing this abstraction of an array as these slots that have indexes, it's an abstraction. It's a high-level abstraction. This is still a bit of an abstraction, but we're getting closer to it. Each of these individual things here is effectively one element in an array. So in terms of, we've got my name written up there. It might be something like FRANKLI ... Franklin in this array that is main memory. So I've taken that array that we've got that's looking at the small thing that's an array itself. I've turned it on its side, and I'm saying that what we've got here is main memory for a process is just this massive array that we have access to. It's still got all the bits and bytes of an individual array inside of it, but it's at the bigger scale here. Any questions about this so far? Okay, good. I will post these diagrams to the course webpage as well, so you'll have access to them that way if you're not able to get it all down here. So to quick summary, there's three major parts of main memory. There's the code section, the heap section, and the stack section. Yes?
Or were you thinking, because if it's multiple tasks, you have multiple.
Okay. This is a single task, yes, yeah. Again, you're in computer engineering? Okay, so there is an operating systems course in computer engineering. I forget what number it is, 37 something. Yeah, yes. And you will see some of this stuff in that course. I know for a fact that you see it in our course because, I spent time talking about lots of this, but you'll learn more there. That's kind of the answer to that question. Good question, but you'll learn more in a different course. Any other questions? Yeah. Yeah. Okay, that's a good question. How about storage? When we're talking about memory, we're just talking about RAM. When you get to 3370, so that's computer organization, and when you get to 3430, that's operating systems, you're going to learn about two things. You might even see this in Comp 2280, and that is called, I don't even remember what that course is called. Does anyone know what 2280 is called? I feel like I should know that. Okay. Introduction to Computer Systems. So you'll learn about something called the memory hierarchy in those courses. And this is one part of the memory hierarchy. Disks and fixed storage are another part of the memory hierarchy. It doesn't really fit into this, though. We can read things from a file and put it into memory, like kind of with code that we're writing, but it's not really part of the diagram that we're looking at right now. Okay? Okay. All right. So I want to focus really closely on the stack section, and I want to see what's happening when we're calling functions. So we've got this code here. We're calling a bunch of functions. We're calling fgetS. We're calling printf. I guess that's all we're calling in this code. We're calling functions, and I kind of want to know what's happening inside those functions, or what's happening in terms of memory when we call those functions. So we're going to be drawing, again, a little bit more pictures to get a sense of what's happening when we're calling things on the stack. So I'm going to keep this open right now. I'm going to put it to the side. I'm going to take this and I'm going to put it to the other side. And what I'm going to do here is I'm going to start drawing what our stack looks like. The stack in our code starts working from the main function. When I call the main function, so I'm going to draw this really big here. When the main function is called in my code, there's going to be space allocated in the stack for two variables here. One of them is an integer that's called argc, and the other one is this pointer type called argv. I'm going to write at the very bottom of this is 0xFFFF. This is the bottom of memory. And we're going to have allocated for us a space for argc and a space for this argv variable. I apologize in advance if you're really picky about straight lines. I cannot draw a straight line, and I also can't be bothered to bring a ruler to class. We've got argc and we've got argv. The other thing that we have allocated for us in this function is at compile time, when this function starts, we are allocated enough space on the stack for this array of characters. So on top of these two, we're going to have an additional 5 elements. This is going to be in the code that we've got on the screen. This is going to be the array that's called name. This is that array right there. At the beginning of this program, it's kind of filled with question mark, question mark, question mark. So if I change this code slightly to be, I want this to be filled with the null byte, then what's going to happen here is that this array will just be filled with zeros. When I call printf, so I'm moving execution now to line 15, what happens is that we're going to push a stack frame onto the call stack or the runtime stack. When we push a stack frame onto the runtime stack, there's going to be some metadata that's added. So I'm going to put another entry here. That's going to have a return address. The return address that's going to be pushed onto the stack here is going to be the address of this line in code. So where we should go back to in the code that's executing when printf has finished. Printf is a function, so we've seen C functions. It's a function that accepts as input a string, which is just a dumb array of characters, and other stuff. It accepts other stuff, but in this specific location, it accepts a string. It's going to take that string. There's a loop inside of printf that's going to say put char, put char, put char, put char, put char. It'll do other stuff, but let's just pretend that that's what it does for now. It'll call put char a bunch of times on this string, and then it will return back to that location. So we have the return address of where we're going to go. The other thing that we have that's been added to the stack, so I'm going to quickly annotate this with this part is our stack frame. This is our stack frame for printf. This array of characters here is not put onto the stack. The array of characters is not put into the stack. I'm going to change this code just slightly. I'm going to call printf this way. Printf takes a string. A string in C is a dumb array of characters. What gets pushed into the stack frame is the address of name. In this code, the address of name starts right here. So I call printf. We're going to add a new stack frame to the stack. Right now we've got main stack frame right here that's got all of the data that has been stack allocated. We call printf. We push this return address onto the stack. We're passing the array called name to printf. And the thing that's being put on the stack here is the address of the array that's been allocated here in the main function. When I call fgetS, I'm going to change this printf back. Whoops. When I call fgetS, we return from printf. This gets popped off. So popped off here means that this is gone. It's removed from the stack. When I call fgetS, what's passed to fgetS on its stack is going to be the address of name the number of bytes it can read of characters, so 50 or 5 in this case, and then a pointer to standard input. And I'm going to actually write this, no, I'll write it as pointer to standard input. The thing that's actually passed, the thing that fgetS actually works with is the address of name. So when we start pressing stuff on our keyboard and pressing enter, when fgetS here is making changes to this array, it's going to start overwriting things in the stack frame for the main function. This is kind of how we're passing something to that function, and it's able to write into that stack allocated array that we have. When I declare an array inside of a function, I get all of its space put onto a stack frame. I'm going to stop here for a second, drink a little bit of coffee, see if there's any questions so far. So I have a tablet here. It's called a Remarkable tablet. I mean, I like it a lot. It's an e-paper tablet. So when I'm drawing, I just see shades of gray, and I don't see this, which is unfortunately, I apologize in advance why it's like, it's just like a maniac changing colors here all the time. Is a nice tablet. If you like to draw on paper a lot, it's nice because it kind of feels like paper, and you don't have to carry notebooks around. But it's also really expensive, and I don't know if I can justify the cost. This one called RMView is an open source implementation of their kind of like desktop application for Linux. It maybe, I don't know. There's other applications. So if you're running Windows, OneNote, or if you're running Linux, something like XOURNAL, Zernal, or Zernal++. Yeah. We'll talk more about that after class. Okay. Okay. Now that we know a little bit about the stack, every variable that we have declared so far has been a stack allocated variable. When a stack frame gets pushed onto the stack at the very bottom of our memory, there's enough space in that stack frame for the entire array that we've declared. Now that we know a little bit about this stack, I want to revisit arrays. An array in C is just an address. It's not even really a data type, it is just an address. In Java, we can return stuff that are complex objects. I want to be able to do that. I want to do that. So what I would like to do is communicate that address to other parts of my program. I want to be able to declare an array and give it to something else. I want to say, use this array outside the scope of my function. I need a new type to be able to do that, though. An array is just an address. It's not even a type. Like, I can't assign things to an array because it's just an address. I need to have a new data type to be able to do this, to be able to send addresses around places. I need to have a new data type that I can use to store an address. So this is going to be a new type that I can use to store an address. An array is not a variable. It is just an address. Please, everyone, chant this with me now. An array is not a variable. It's just an address. Okay, one more time, please. An array is not a variable. It's just an address. Okay, I want to really quickly say one thing here. When we think about arrays, we think of this as element 0 of the array. An array is not a variable, it's just an address. The element 0 in the array is actually just that address plus 0. Element 1 in this array is that address plus 1. Element 2 in the array is that address plus 2. Element minus 1 in the array is that address minus 1. An array is not a variable, it's just an address. A pointer is something that I can use to have a value. It's an actual variable. The value of the variable is an address. An array is not a variable, it is an address. A pointer is a variable whose value is an address. All of the data types that we have can be declared with this modifier asterisk. An asterisk says, this is a pointer to this kind of data type. I can use pointers to send addresses around between locations. This line here, this is a variable that's called val, that's a pointer to type int. When I look at the address that's stored in this variable, it will be an integer. This is a pointer that's called val to type char. When I look at the address in this variable, I can treat it as though it's a character. This is a variable called val that's a pointer to type float. When I look at the address in memory that's stored inside this variable, I can use it as a floating point number. I can't return an array. An array is not a variable, it's just an address. But I can return a pointer. I can return an address as a pointer. I can store the address in a pointer. I can store the value that is an address inside of a pointer. In other words, I can give you the information you're looking for. I can't give it to you directly as an array, but I can tell you where in memory to look for this. I want to go back to our strings.c code right now. And in the last couple of minutes of class, I'm going to get started on this, and I know that you're all going to be sleepless thinking about what this is going to look like, but I'm going to start it, and then we will get back to it tomorrow. So I'm going to quit out of line input, and I'm going to edit strings.c. I'm going to scroll down here to my string copy function. This is the one where we have the place that we're copying from, the buffer that we're copying from, the buffer that we're copying to, so source and target. It returns void right now, and we're accepting how many characters I want to copy. What I'm going to do today is change the signature of this function. That's what I'm going to do. So I'm going to delete the word void. I'm using vim. If I want to delete the next word in vim, I can do that by pressing D to start deleting, and then E as the end of the word that I'm on right now. So DE deletes what's under my cursor up to the end of the word that I have. I'm going to change the return type of this to be char star. What I'm saying right now, by changing the signature of this function, is that I don't want to accept a target as input. I just want to have a source, the thing that I'm copying, how many characters I should copy from it, and what I want to return is the address of where the copy is. My function will still copy something, but I'm going to give back this information by telling the caller where to look. This code does not compile right now, but I'm going to leave it like this. I'm going to post it. It will not compile. I will mark it in the README. A tiny aside here. When I've got these lectures that I'm posting, I'm always putting these README files alongside of it. These are good examples of what a README that you write can look like when you're submitting code for an assignment. So a brief description of what the program is, a brief description of how to compile and run it on the command line. Very short. It doesn't have to be super long. I want to leave you with one thing here. I'm not asking this question right now, but I do want you to think about it. I want you to think about all the features that you have used and seen in Java that makes reading from standard input a quote-unquote safe operation, and some of the things that we have seen in C that makes this a quote-unquote unsafe operation. Just thinking about this. We'll revisit it tomorrow and later, but for now, let's just think about it. At this point, you should be able to get line-based input from standard input with fgetS. You should be able to manipulate the data that you get back from fgetS so that it terminates correctly. And you should be able to know what to do with lines of input that are longer than what you're expecting. And the answer right now for what to do is just be told how long the longest thing is that you can expect and make a buffer that's big. You can do this, write code that takes advantage of its environment through redirecting of standard input and output for file I/O. You can do the standard input part. We will eventually talk about the output part. You should be able to describe the concepts of in-memory management, in-application memory management, such as the runtime stack and the heap. You should be able to visualize and describe parts of the standard memory layout. So for now, very specifically, the code segment and the stack, what kinds of things go in there, what is in there, and how does it change as a program is running. You should be able to visualize and describe how the stack changes as functions are called. We're going to continue looking at this tomorrow. Thank you all for coming out, and I will see you tomorrow. Bye, everyone.